Hello, everyone, and welcome to another webinar from Optiwave. Today's webinar is about revolutionizing PIC system characterization and machine learning tool in OptiSystem 22.1, a new version released a few weeks ago. We'll talk about new components and features. My name is Ahmed Atiyah, and the webinar, I'm gonna give an overview about Optiwave, then I'll describe the software product line of Optiwave. I'll showcase the new components, discuss the new improvements in this release. Then I demonstrate the operation of this component in OptiSystem. Then we're gonna show you a demo of the machine learning tool, how to operate this newly added tool in OptiSystem version 22.1. Okay. Optiwave is basically established in 1994. It's over 30 years ago, and it's located in Ottawa, Ontario, in Canada. And Optiwave mainly developed software tools for designing, simulating, and optimizing components, links, systems, and networks. And our software basically give advantage to users to shorten the product line for introduction into the market. It improves the product quality as well as cost effectiveness through the conducting the simulation ahead of manufacturing and or making the circuits or photonic integrated circuits or a device or modules. Optiwave software product line is divided into three categories. One is the system level, which is supported by the OptiSystem software, which we're going to talk about it today. And OptiSpice software is an optoelectronic software, can talk with OptiSystem cohesively and used for designing and simulating photonic integrated circuits. The other category is the component level software, which includes the finite difference time domain, FDDT, OptiMode software, as well as OptiBeam propagation method, OptiBPM. And then the OptiFiber for designing different types of fibers and OptiGrating. The last category is the instrumentation software, which enables users to automate characterization setups. So it can talk to any equipment and can set up equipment, do measurements, and collect data. And this data can be either processed internally with the software or can process externally. Optiwave, as I mentioned, it's over in business is over than 30 years. We have over 3 million downloads of the software. Our customers are in over than 80 countries in the worldwide. We license the software into universities, research and governmental institutions, and academia. This is a snapshot of some of our customers in industry as well as in university and academia. Optiwave software can be downloaded from Optiwave website, so optiwave.com, and you go to the download page. Then you click on the 30 days evaluation. After that, the pop-up window gives you the registration page. You need to use a legitimate account through your corporation or through your academia institution. And then register. After that, you set up your password, and then you have access to download any of these 8 software packages. And these software packages can go to the program files on your C drive under Optiwave software. Now, this is an example of different software packages downloaded in the C drive or program files, as I mentioned, Optiwave software. And specifically for OptiSystem software, you have 4 main directories, including the component library, the documentation, which is an important resource. It's great to go over it, and especially it has the information about the release notes, which describes the changes, additions, bug fixes, and many more information, in addition to the user manuals and reference manuals and so on. There is a good resource for users on our YouTube channel. It's Optiwave High Definition channel, and you can there view different videos and webinars related to the different products, as well as you have on our website a knowledge-based page, which you can look into different examples demonstrating the either published papers or different designs in the different fields using OptiWave software. Now, I'm going to talk about OptiSystems components in general, quickly go through them. We have over 625 components so far in version 22.1. And this including sources. We have different models for the sources, either analytical models or models in which you can use measured data into them to make the component more practical. And then we have LED models, VCSELs, DFBs, Fabry Bureau, white light sources. Modulators, we offer analytical models, Mach-Zehnder modulators, or a single drive or dual drive Mach-Zehnder modulator with single port or dual port, as well as electro-absorption modulators. There is an analytical model as well as a measured model, which you can load measured data in it. There is phase modulators, amplitude modulators, as well as frequency modulators. A bit sequence generator, which is different components can be used to generate sequences, random sequences of bits or user-defined sequences of bits. Even you can load your own sequence of bits generated, let's say, for example, from an equipment. You can load it into these components and use them in the simulation. There is also test patterns used for compliance, for jitter analysis, and so on in the system. Modulation formats in OptiSystem, we support almost every modulation format in the field, from standard no return to zero, to carrier suppress, return to zero, dual binary, differential, phase shift keying, any type of phase shift keying, any types of QAM up to 256 QAM. PAM, we can generate any type of PAM, PAM4, PAM8, even non-standard types like PAM3, PAM5, PAM7. Pulse position modulation, as well as probabilistic amplitude shaping, where you can control the probability of each symbol in your transmitted PAM or QAM signals. Optical fibers, we support different models for single-mode fibers and different models for multi-mode fibers, in addition to multi-core fiber and photonic crystal fibers. And now you can design these types of fibers in OptiMode software, so you can have any type of structure of the multi-core, any type of refractive index, trenches, and so on. You design them in OptiMode, you get your fields, you export them into OptiSystem, and then you do crosstalk calculations, and then you do it in analysis in OptiSystem for transmission. The same thing for photonic crystal fiber, hollow core fiber, and so on. In terms of filters, we support any types of filters, from analog filters or digital filters, as well as electrical and optical filters. We have fiber Bragg rating filters as well. Modulators, electrical types for orthogonal frequency division multiplexing, and quadration modulation for intermediate frequency for, like, for example, 5G or 6G applications. Optoelectronic circuits with the addition of using OptiSpice software, you can do laser drivers and ring resonators. We're going to show you some designs right now in OptiSystem using the new components introduced in this release. There is switches. We did webinars with Lucida a few weeks ago using the cross-connect switches, using the new components, which is OptiLucida component, co-simulation. There's interconnect you can do. Photonic integrated circuits, the new components we introduced there, it's called PIC waveguide, and the other one is called optical S-parameter components. Also, we have signal processing. So you have digital signal processing, very sophisticated component, which can do lots of functionality in it. There is equalizers, adaptive equalizers. There is regenerators for time, for clock recovery, for data recovery, as well as 3-hour generation. And there is FIC support. So we support Reed-Solomon algorithm, as well as low density parity check. There is bit mapping, which enabled actually the probabilistic amplitude shaping and any other application you require. Detectors, we do have bend detectors, which can take measured data in it. It has a very also sophisticated models for noise analysis, thermal noise, shot noise, and any other type of noises. There is avalanche photodiodes. There is single photon detector. and photon number resolving detector. So these components can be used for quantum applications. We demonstrate that in different webinar. Optical amplifiers, we have a huge library of doped fiber amplifier, doped fiber components, which you can build your own amplifier from scratch using the doped material, so erbium, ytterbium, or co-doped erbium, ytterbium, or doubly clad erbium, ytterbium. So there is stolmium, baridium, holmium. There is other modules, gain blocks. There is a semiconductor optical amplifier, Raman amplifier. There is waveguide amplifier for erbium, ytterbium, co-doped. And also there is components to do gain flattening optimization, which we're gonna describe it a little bit later on in this webinar. Electrical amplifiers, we do have transimpedance amplifiers, which can work in the linear regime or nonlinear regime, as well as limiting amplifiers and automatic gain control. Passive modules, you can, what devices or modules you could think of, it's available in OptiSystem, from couplers, muxes, arrayed waveguides, switches, attenuators, circulators, polarization controllers, and so on. There is mirrors, there is reflectors, electro-absorption reflectors, and so on. Multimode applications, we have multimode, different models for multimode fibers, multimode amplifiers for erbium, doped multimode, or ytterbium multimode fiber. There is mode generators, which you can generate modes after, let's say, CW lasers. Then you have passive components, which are supporting the multimode application. There is spatial visualizers, which you can demultiplex the multimodes and evaluate each mode separately. There is optical channel. We support the fiber, which is the basic channel. Then the Li-Fi channel. We support satellite channel. A free space optic channel. We have a sophisticated component. We call it universal FSO, which has it can do temporal and as well as spatial analysis of the beam. So you include weather conditions, include scintillations, and as well as beam progression. You have phase mask. You can do turbulence effects spatially as well as temporally. Now, there is a visible light communication channel and as well as underwater channels, which is line of sight and non-line of sight, which take into account the effects of water, salinity, temperature, and so on. Visualizers, we have a huge library of visualizers in the optical domain, electrical domain, binary, memory. There is BERT, as well as some equipment for light wave analyzers, like vector analyzers, as well as filter analyzers, and so on. Most of the components works in bidirectional, and as well as unidirectional, so you can transmit signal over them from west to east and east to west. Now, there is a tool in OptiSystem software which is used for optimization, and this can be used for optimizing a single parameter in your system or a multi-parameter in your system. There is the gain flattening filter, which is used for mainly for amplifiers. You can flatten the gain across, let's say, multi-wavelengths. And there is also a Monte Carlo yield estimation optimization algorithm. There is the new tool which we added up here. I'm going to talk about it today. It's the machine learning tool, enables you to train, test, as well as predict system performance based on eye diagrams. Now, the tools can be accessed from the OptiSystem GUI in the toolbar under Tools, and then you can have optimization. When you click on it, you have the window, and you start to choose which optimization algorithm you need, single point or multi-point. Double click, and then you set it up. There is a webinar, we talked about it. If you're interested, let us know. And then you can also access this window through the calculation window. So if you go under optimization, you click on it, you also have this access of this window, and you can set up the optimization. To do the calculation of optimization, you need to select the run all optimization, and then you would have access to also to view the optimization progress through some plottings. The new tools for machine learning tool, once you click on it, there is a pop-up window comes up, which has many tabs here, enables you to set up the training method, as well as to view the results after training or after testing, and as well as prediction. In terms of OptiSystem applications, we have many applications. We have an example library which has over 1,000 examples. They are categorized in different categories based on the application. So you have advanced modulation directory, includes different examples on QAM, PAM, pulse amplitude modulation, phase shift keying, and so on. There is examples on radio over fiber, on front haul 5G applications, optical amplifiers, lots of examples in the optical amplifier library. You can see it here. And then there's laser design library as well, in the optical amplifier library. There is a directory about microwave photonics sensors. We have different designs of OTDR, Phi OTDR, and FPGs, tilted fiber Bragg rating, photonic crystal fiber sensing and biosensing, and so on. For wireless channels, we have different examples on free space optics as well as underwater communication. There is examples on spatial division multiplexing for few mode transmission or multi-mode transmission. In single, you have single mode and multi-mode, multi-core applications. Quantum key examples, if you are interested, let us know. We can pass you examples. And then digital image processing, as well as the new directory on photonic integrated system characterization, which is something new we added. And there is also directory on machine learning example. In OptiSystem, as I mentioned, we have over 625 components and visualizers. We have over 1,000 examples in the example library, which can be used as a basis for testing as well as building new projects on these examples. Now, one important thing about OptiSystem software is interworking with other software of Optiwave. So OptiSystem works with OptiGrating, with OptiBPM, with OptiSpice, OptiMode, OptiFDT, as well as OptiInstrument. So you can generate results in these softwares and include them in OptiSystem for simulation. Also, OptiSystem can work with external software like MATLAB, Scilab, Python, C++. And this addition also we did like in the release 22 is adding up OptiLucida co-simulation component, which enables you to import designs of photonic integrated circuits from IPCAS software into OptiSystem and then do system characterization for photonic integrated circuits. Now, OptiSystem can be called from the Python or MATLAB or other software externally, or can call this software from OptiSystem. So you can have two ways of communication between OptiSystem and this software. Either we call it from OptiSystem or we call OptiSystem from these software packages. Okay, now going to our main part of the webinar, which is about the new components in OptiSystem. As I mentioned, we have the optical S-parameter component and the PIC waveguide. Now, optical S-parameter component, as you can see here, it is doesn't have any ports, and it's dynamically setting the ports based on what you load into it, the file you load. It can accept files from BPM software and FDDT, as well as from any equipment or any other file like S-parameter file in the touchstone format. The PIC waveguide component is basically the component which it's a waveguide, optical waveguide, but can be controlled electronically from single port or dual ports. I'm going to show you some examples later on how to operate these devices and build many circuits with it. Now, the tool, as I mentioned to you, this is the machine learning tool, which is new in the OptiSystem. About the release note documentation, you can find it under the C drive program files, Optiwave software, and then the documentation. This is a very good resource. If you need to, like whenever you download the software, is a good idea to go over this document because it has the list of new components, the improvements in this release, the documentation changes, as well as the bug fixes in this release, in addition to the newly added examples into example library. Okay, and then the other part is the resources in terms of the component data sheet. The component data sheet can be accessed when you double click on the component, you get up the property window, or you can right click on the component and choose component properties window. You can access the data sheet through the help button here, or you can access it from the OptiSystem component library in the documentation. or even you can access it from the Windows Start, and then you scroll to OptiSystem documentation, and then you have all these components available there, and you can see the datasheet. You can do the search per name of component. The improvement in OptiSystem, this is a list of these improvements. I'm gonna talk about a few of them. One of them is the Spatial Demultiplexer. This is, as I mentioned, it allows you to monitor the modes in a multi-mode transmission system. So when you do one thing which it used to be, when you do a multi-mode amplifier, the ASE was calculated based on the first mode, so you can see it only on the first port. Now, in this improvement, we allow the user to view the ASE produced for each mode generated in the system, and it's a separate board. And that is very, very important because some modes will be having higher power, some less power, and more dominant modes compared to the others. So this is give you a better now visualization process. The other part which we did improvement here is the erbium co-doped waveguide, which is before it was crashing when you do feedback into the waveguide to, for example, if you want to do a laser based on this erbium waveguide, the system is not able. But now after this improvement, you can build erbium co-doped waveguides. VCSELs, we allow the users now to manipulate the chirp in a negative way, not only positive, and by changing the range in the component. And we will have a webinar jointly with Corning on June 11th to talk about this feature, about how the chirp can be controlled and managed and affecting the performance of the system. Then the other thing is the project browser. It's we added up in the display of the visualizers. Like if I go here into OptiSystem, if you go, for example, this PR analyzer, and you go into the graphs, and you go to eye diagrams, so we added up a feature here. As you can see, you can scroll through the different iterations when you do the sweep iterations of this system, as well as you can do also all iterations in a single chart if you wanted to do it. And in the other thing we did also improve we added up into the BERT analyzer, we made this feature here true, because before it was only displaying the Q factor, but now what you see the Q factor display as well as the I in a single shot. Okay, so going back here, let's go into the next one here in the bug fixes. I mentioned about the erbium co-doped waveguide enabling the laser designs. Also about the OptiReceiver component, there's some cases there was issues with the port location, but now it's been fixed automatically. And then there is some improvement on displaying the normalized radial population density in the multimode erbium and ytterbium components. Also the FSO channel, the universal FSO channel, we had improvements on performance of these components. Before it wasn't enabling dual polarization, but now it can work with dual polarization or single polarization, as well as with the multi-wavelength transmission. So this is a kind of improvement. In the first version, when we introduced it, it's only working with single channel, but now you can use DWDM channels as well as dual polarization and so on. Another improvement here we did is the PHY OTDR. When we introduced the PHY OTDR, it was a standalone component, and it was released in release OptiSystem version 16. But after that, there was some issues with the code, and it wasn't working properly. We fixed it, and then we introduced a component, not in this release, it's going to come up in the October release, which we call it Universal PHY OTDR. And that component will allow you to use the other components in OptiSystem, basically. So you can use your own laser sources, pulses, amplifiers, and so on to do the sensing applications. Okay, and the last thing is about the dual port OTD, optical time domain visualizers. In some cases, like for example, if you go into this case here, if you don't have a signal on the other port of the dual port analyzers, like in this kind of scenario, you have a crash on OptiSystem. So this has been fixed. You must have before a signal always on the ports. As you can see here, you have to put a null. But now this issue has been resolved. You don't need to worry about the crash in OptiSystem in that scenario. Okay, next is the examples. So we'll start with the first is this example about the ring resonator impulse response. So we can use the optical S parameter component and the PIC waveguide here to build a ring resonator. So you can have a coupler here. You can control the separation, the length of these waveguides here, and then the waveguides of the straight part. And then you can build ring resonator, single one or multi-one of them. And then you can study using a impulse response here. You can have a single pulse going into an optical impulse generator. And then you can look into the impulse response of these dual rings. And you can look at the performance on the through channel or drop channel and so on. Another example is about, for example, here you have two DWM channels, and you can use the ring resonator here with, like, for example, if you look here at the combined channels, then you can look at the through channel. One of these wavelength, which is this wavelength of the laser, is going through. The other one is blocked because it's going to be dropped on this path here. And you can, from here, study the effect of crosstalk, how much is the ratio between the input and the other one, which is going to be leaking. So you have to choose properly your filters afterwards and so on. So this is going to give you a lot of freedom to do analysis in a DMUX structure of a ring resonator. So this is the other one, which is here. And then if you measure it on the other port, on the through port, you can see it appearing on this side here, and the other one is how much is power level compared to this one. Also, you can study it. Another applications of these components is the waveguide. As I mentioned to you, it's an optical waveguide, but you can control it using electronic ports, either single port or dual port. So the component itself has, in this field here, PIC waveguide mode operation. You have single optoelectronic or dual port optoelectronics control, or you have no control, basically as a straight waveguide, optical waveguide. And then you can control the refractive index either from a constant, or it can be from a file. So can you load your file, so can generate a wavelength-dependent refractive index control. And you have also polynomials. You can control the electrical control of the refractive index, and there is different ways to control using polynomials. You can control the refractive index real or imaginary, or the length, or all of them. So it depends on how you need to manage your component. And there is different examples we created in example library in this release. One of them is how to control refractive index here electronically, and then you pass the electrical signal into the optical signal, as you can see. And then we build example for Mach-Zehnder interferometer. So you have two waveguides, and then you control the length of each waveguide, and then create some kind of mismatch, and then create an interferometer by controlling the arms. In this example, in OptiSystem, we swept the length of this waveguide, and then looked at as you can see here, the length of the other waveguide, and looked at the frequency response of this interferometer. You can see here, in this case, there is 300 micrometer on this arm, 500 micrometer on this arm, and then this is the frequency response. Another example we introduced in this release is the PIC waveguide Mach-Zehnder interferometer, Mach-Zehnder modulator. So you can have two waveguides here with certain length, but you control the refractive index of one of them. So you apply an electrical signal here, and then you modulate the laser with it. So this kind of example, you can see here, there is a file we load. These files are in the example library. You can see them under the example library of inter software working. And this is the structure of the file we load here. So you have a wavelength here in micrometer. You have the refractive index real, refractive index imaginary. And then eventually you can modulate the laser. So the amplitude of this signal, as you can see, it has a DC bias around 600 milliamps. And then you apply it into the waveguide, you control the refractive index, and then you modulate the laser and you generate the modulated signal at the output of the Mach-Zehnder modulator. Another example here is controlling the refractive index, wavelength dependence refractive index of this waveguide. So what happens is if you apply a signal at two different wavelengths, as you can see here, then you can see the effect of delay or phase shift in the waveguides on the output, as well as you can see the delay. So you can see with this dual port visualizer, how much is the delay between the input pulses and the output pulses, as well as the delay between the two ports of these two signals. Okay, so you can see here this file in OptiSystem example library is a wavelength dependence refractive index, and this is just only for demonstrations. It's not a practical example, but you can do your own designs and import these files into OptiSystem component. Now, as you can see here, the mode of operation is optical. And in this diagram here, you can see the difference between the port of this signal at this port and the output of the propagation through the waveguide. And you can see like this pulse is 1, 1, 1, 1, 1, and this structure, there is some delay to start responding. And also, you can see if you put the difference between the two wavelengths at the output, you can see there is some delay between the two responses because of the wavelength dependence refractive index. Okay, so next here is the machine learning tool. The machine learning tool, there is an example we added up into OptiSystem example library, and we built it based on an example in the introductory library, which is lesson 4. So you can see it's a very simple example, but what we did in it, we scanned or swept the length of the fiber in this between 50 kilometers to 75 kilometers, and then we monitored the Q factor as well as the BER of these signals at these different lengths. We swept it 1,000 times, and then we trained the system and tested. So I'm going to show you in a few minutes a recording of the whole process to enable you to follow the steps and then build your own system and do the machine learning functionality in OptiSystem as needed. We require your feedback, please. If you have any feedback about the tool, we are in process of improving it because this is the first time we introduce it in OptiSystem. So your feedback is really appreciated about the performance of this component of this tool. As you can see here in the tool, just mainly, just quickly, there is current machine learning training set. So you have to build your parameter setting here, the algorithm. We have one algorithm. We are in process of adding 2 more algorithms. At this time, we support diagram of 2 levels. We're going to support multi-levels as well. In this fields, we allow the user to control how many images used for training and how many images used for testing. In the code right now, there is hard-coded validation percentage, which is 20% of the training images. We're going to expose that parameter to the user in the next release. Then we have the number of layers. You can control dynamically the number of layers. The default in the component right now or the tool is 5. But once, depending on your application, you can set up dynamically the number of layers, and you can choose every layer what it is. So I'm going to leave this part to the demo and basically go from there. So I'm going to share the demo for few minutes. It's actually about 19 minutes. And then after that, I open up for, conclude the presentation and then open up for questions. Okay, thank you. So I'm going to mute myself during this part. Hello, everyone. This is a demo for the machine learning tool added up to OptiSystem 22.1. And to operate the tool, what you need to do is you need to go to OptiSystem and create design a project. Now, in OptiSystem example library, we added a project in the machine learning tool directory. And this Project is very simple. Project, straightforward project. As you can see here, you have a laser which is externally modulated with non-return to zero pulses, and then running at 10 gigabit per second. Then we have a fiber. This fiber right now we are sweeping it. So the fiber, if you check on the sweep, we sweep this length between 50 kilometers to 75 kilometer, and there is 1,000 steps. And then we detect the signal, transmitted signal. We low pass filter it to get rid of the high frequency noises, and then we analyze the signal using the BER. The machine learning would be training the system through the eye diagrams, and then we'll be able to predict the system metrics through the eye when it's loaded into the machine learning tool. So the process to make the machine learning tool is first you design the project, and then you calculate the project. So we have here, as I mentioned, 1,000 iterations. The first step is to calculate the project. So we have to calculate the project. It's going to take a few minutes, depends on the computer you are operating. And then once the calculation is done, we launch the machine learning tool from the toolbar, and then we start the process of setting up the tool. Okay, so I'm going to pause the calculation here and the recording. Just pause the recording just only to save time for the recording. Okay. Okay, as you can see here right now, the calculation is about 770 or 780 sweeps out of 1,000. It needs few more minutes to finish. And then I'm going to pause again, and then we continue once it's done. Okay, so the calculation now is done. What we can do, I would like to highlight a few things here. So if you go into the BER analyzer and under graphs, and then you go to eye diagrams, if you double click on it, you can see this is a new feature we added up into OptiSystem 22.1 is the user can scroll through the different iterations in the sweep here, as you can see, and they can take any screen, or you can do all the iterations at once in one full shot. This is one thing added up. The other thing is just want to highlight here is if you right click on the eye diagrams or any graph, you can create a movie or you can create frames. Now, if you go into the frames again, just to highlight a few things here also, you can see that the frames created with labels, with units, with also numbers here. When we do the machine learning training process, these kind of images, the first step is to prepare them, where we remove all of these labels, units, axis, and so on, and just keep the traces of the pulses received, and then we digitize them and do the training afterwards. So now we're going to start the process of training. So you go to the tool, you go machine learning tool. This is a pop-up window. Typically, when you start any project, like for example, if you start a new project and with the tool from scratch, this is how it looks like. The default is 5 layers here, and these layers, what you can do dynamically, you can choose the number of layers, and then you can choose the type of layer of every the type of the layer based, like for example, this is convolution, this you can do it dense and max boiling. It depends on the algorithm you are using. And also here you choose the algorithm, which is at this moment LNet. We're gonna add 2 more algorithms by next release, expected in October. Then right now also we support 2-level eye diagrams. We're going to support multi-level eventually in the next release. The field here is the ratio of training images. The user will set up this number. If this default right now is 70%, which means 70% of the frames created will be used for training. We have 1,000 frames, so you're going to use 700 frames for training the algorithm. And then there is a built-in feature right now. It's hard-coded. We're going to expose it in the next release. where do validation. So 20% of the 700 images, which 70%, is going to be used for validating the algorithm. And they are selected random images, like 20% of the 70%, which is like 140 images. And then eventually here you choose the compression ratio of this frame. So every image has certain size, and then you can do some compression on it and the number of layers. So now in the example, let's go back again to the example. The example which we did calculate here, if you go to the tool again, in the example library, we have stored one algorithm already for this example. You can add or delete the machine learning setting here. So for example, if you need to change some parameters, you create a new one. So when you do definitions, and then you do the calculations later on based on the setting in that specific machine learning like file. Now the second tab here is the tab where you choose the parameters. So all of the components in the layout of the project, which you can see here, are present here. And you can access the parameters of these components. So for example, in this example, we do the training for the length of the fiber. Typically what you do is you to be able to access that parameter in the training, you highlight it, you can add it up here, or you can double click on it and it goes into the selected window. If you want to delete it, you just delete it from here. Now, once it's selected, all the values of this parameter is going into these fields. So you can scroll in every parameter here for the values. Now, in the second, in the next tab here, it's the results, which is used for the training also. Now, in this system here, we train the system in this example for Q factor at minimum bit error rate and the minimum bit error rate. How to use it? As you can see here, only the components with results appears and you can expand it. Other components with no results you cannot expand it. In this example, we use the results from the BER analyzer. You choose the, for example, the minimum bit error rate and the Q factor at minimum bit error rate. You can move this windows to the right if you want. And now if you click on it, the same scenario here, you can look at the different values of every frame, basically from 0 to, or from 1 to 1,000. Same thing for Q factor. At every number here, you can see the value of the Q factor. Next tab here is the graph, which is, as you can see again here, any component with the graphs is you can access it and use it for the machine learning process. At this moment, we are using the eye diagram for training in this algorithm. So we go to the graphs and we select the eye diagrams. So if you go into eye diagrams here, highlight it, double click again, the same scenario, and it goes. Once it's added, the first step after you select the graph, which you need to do, you need to prepare the iteration frames, which means you need to remove all these labels. This process takes a few minutes, so I'm gonna run it. And as you can see here, you have to pick up a folder where these frames is gonna be going. So if you go to the example library, I created in the machine learning tool here another folder, just empty folder, and you select it. And then now the process is gonna start where every frame is gonna be removing all these labels and prepare it. It's gonna take a few minutes, as I mentioned. I'm gonna pause the recording until it finishes, and then we continue. As you can see now, the progress bar is around 38%, and it's gonna take few more minutes to reach 100%. Once it's reached 100%, we go to the next step, which is create the iteration frames. So I'm gonna pause again. Okay, now the preparation iteration of frames is 100%. What the next step would be creating iterations of frames. So you click on it, and the process starts to digitize, compress, and do preparation of all of the frames for the training process preparation. So I'm gonna also just hold for a few minutes until the process starts to show you the progress. Okay, so now the process started for preparation of the iteration of frames, and as you can see here, it's gonna go over all these frames, the 1,000 of them, and then once the process is done, you can see the path for the file we used for preparation, and we're gonna see these images gonna start prepared and loaded in the basically the folder where we're supposed to save them. Okay, so now it's like 136 and so on. So this again, we're gonna pause right now, and then we continue after it finishes. Okay, so now the preparation for the 1,000 frame reach the end, and then the last step is gonna be happening. As you can see in the file below here, we have the 1,000 iteration frames. Once this process is done, okay, now it's done. If you double click on one of these images, what you can see here, you can see all the labels is gone, the units gone, scaling is gone. It's just only the traces of the pulses received by the eye diagram. And now we go back again to OptiSystem and do machine learning tool. Now it's everything is done in this tab. We need to go to the training tab. The training tab here, as you can see, there is a tree here where it describes the parameters. For example, this is the main parameters. We have machine learning algorithm LNet, 2 levels, ratio of training images is like 70%, and so on. You can move this away. And image compression ratio 40%, number of layers is 8, and every layer what it is constructed of from, and so on. Now, once you click on training, you can look at eventually once done the 2D and the output. So let's try the training process now. So once you click on the training, it's going to be pop up the window where they start executing the algorithm. And now the process, once it's started, okay. So I'm going to pause until the process finishes, and then we continue from there. Okay, so now the calculation has been done for the training, and then you go to the graph here tab, and you can expand the main auxiliary main axis, y-axis, or the auxiliary axis on the other side, the right display, and then you can start right now for example, the loss for calculation, and then for example, for the calculation, and then you can also see the epoch versus mean error, mean square error. And so, for example, if you do, this is the epoch versus validation loss. So you can see if you do the epoch for loss and the validation for loss, that's the difference. There is some spike here for the calculation. But if you do, for example, the mean square error, and then the mean square error after validation, which is, as I mentioned to you, about 20%, there is this some behavior here with epoch number 20. And now details on the results, you can see them here. So it can give you the layer description, the parameter used, the compression and everything. And then also the results here for every epoch, the parameter, the values obtained, which is summarized in these graphs, basically. Now, the next step is to use this trained model and do the testing on the remaining images, which is 30%, like 300 images. Now, if you do the testing, you select testing in here, and then the window pop up for the processing. And once the testing is done, we can take a look again on it. I'm going to pause the recording here. The testing has been done, and then you can start looking into the results. The same scenario, you have display on the y-axis main, and then the which is the left, and the right, which is the auxiliary. And then you can see, for example, the actual length, which is being tested, and then the predicted length from the model. Also, you can look at, for example, the error in the, for example, here, if you go error in the length, this is the error in the length, like in about in meter or less meter, depends on the disk values, could be plus or minus error. Same thing for prediction of the BER. So, for example, this is the Q factor, actual Q factor values, and this is the predicted Q factor when using the model. They are, if you want to look at the errors of the prediction, you can of the Q factor. So error in prediction, and this is the values, is less than like 1 in the Q factor, mostly is around 0.2 error. And then if you, same thing you can do with the BER. So this is kind of the graphs. You have also the results, which is displayed here. This is the length of the fiber, this is the Q factor, and this is the BER, and this is the predicted values. So you can, if you wanted, you can download them for further analysis. Now, the last tab here, as you can see, this is user predicted result, and this is works with the last button here. This button here, you need to go back again to the graph, and then here you need to load an eye diagram, for example, and from this eye diagram, you run the prediction, and then the system will give you the length of the fiber used and the BER and the Q factor, which you did train the system on it. So I'm going to pause here for a second to generate show you how to generate an image, and then we do the prediction together. Okay, so go pause here. Okay, so now what we need to do, we need to load a graph or an eye diagram, and this eye diagram, we can go into this image here. This image, if you, just to show you this image ahead of time, this is the image which was generated with the example. So this has the regular image, which has amplitude, time, and eye. And then from what we're going to do, we're going to load this image, which we don't know what is the conditions being taken this eye from. And then we will allow the system to predict the condition, which is the length of the fiber, and then provide the Q factor and BER for it. So let's go there. We're going to load this image, and then we generate prediction graph. So it's going to take a few minutes to generate that. Once it's done, we go to the prediction tab and we launch the predictor. Okay, so now we go to the testing prediction and you use a prediction. So this prediction now it's gonna run, and then once it's done, we're gonna take a look at the parameters, which is length, and the results, Q factor and BER for that specific eye loaded. Okay, so now you go to user predicted result here. So the Q factor is 60, and then the length is 60 meters, 60 kilometers, and the Q factor is 5.25, and bit error rate is 1.610 minus 1. So that's how it's the process is going to be done for using the machine learning tool. So with this, I thank you very much, and then we continue the webinar. Okay, thanks for listening, and then let's continue the webinar here. So next is just only a note here that you can download OptiSystem 30 days free trial from our website, as I described to you earlier, and you can check for the new release advantages. So now I'm done with the presentation, and I'm open for any questions. Thank you very much. So there's a few questions here. If you have any question, please don't hesitate to email me at ahmed.atiyya@optiwave.com or at support@optiwave.com. And If you have any feedback on the machine learning tool would be appreciated. As I mentioned to you, the tool is new and introduced for the first time here, and we need your feedback for any comments. Okay, so there's a question here about are you able to train the system for single value results without eye diagram? So the machine learning tool right now, it can work with the eye diagram. So you need to load an eye diagram, but however, you can put any parameter with it to be trained. Now, in the next release, we're going to allow independent training without a need for image to be loaded with the machine learning tool. There is another question here. Can you load measured data for the big devices into OptiSystem? So this optical S-parameter component can accept an S-parameter files. You can generate them using or collect them using network analyzer, or you can have them from another simulation tools and load them into OptiSystem and use them to characterize the photonic integrated circuit. Another question here, can I simulate distributed optical fiber sensor using OptiSystem? So the OptiSystem, you should be able to use different components in OptiSystem for sensor applications. There is the tilted fiber Bragg rating, the fiber Bragg rating, which has temperature sensors as well as stress and strain, and the Phi OTDR. The Phi OTDR at this moment, the pulses shapes and power conditions and laser conditions, everything is built within the component. It's working in this release 22.1, so you can use it. However, as I mentioned, you would be able to use a release coming up in October with a component called Universal Phi OTDR, and that component will enable you to do distributed sensing with any type of signal coming into it. So you can generate your own signal from scratch using the other component, lasers, modulators, and so on. Another question here, can you share the recording of the meeting? So what we're gonna do, we're gonna post the recording for the machine learning on our website as well as the YouTube channel, because it's very important that you can follow up the procedures to do the training and the testing and prediction. Again, please just, if you have any feedback, don't hesitate to send an email to us, because this is very important for the development process. Okay. Another question is how to see the depth through the ring resonator after doing the modulation. So in the component, that's the good thing is about the design of the components. As you can see in the example, for example, we built and it's an example library. There is two waveguides creating either the Mach-Zehnder interferometer or the Mach-Zehnder modulator. You can play with the structure, either refractive index profile or the length of the waveguide, and control the spectral characteristics. And we showed you can apply an impulse at the input of this structure, and then you can look at basically the depth of this ring resonator. So you can design the ring resonator based on your applied signals, wavelength, and so on. So these things, the flexibility, you can basically you do it through sweeping functionality or some kind of optimization feature in OptiSystem. Another question, what will be the output through the photodetector? I'm not sure what it means. It is the same follow-ups from the same attendee. The photodetector, which is at the output, if it is the ring resonator output, then you have the spectrum analyzer to look at the spectral characteristics of it. Also, you can have a power meter if the power meter is in front of it, a filter, you can set up the filter at your desired wavelength, and then basically design the ring resonator to give you the maximum power at the power meter. So this would enable you to kind of optimize the design using only power meter and the filter. Another question here about can we design multimode erbium doped fiber in OptiSystem and monitor ASC for each mode? How many modes you can support? Okay, so as I mentioned in OptiSystem version 22.1, we added up the feature of the spatial demultiplexer where you can monitor the ASE pair mode generated in the multimode fiber. Now, in the multimode fiber, it depends on the structure of the of the fiber. You can support up to seven modes which you analyze. However, you can see more modes which is kind of ignored in the analysis. So you can follow the analysis of 7 modes, but main modes, but and they are degenerate modes, by the way. So you can look in principle 14, but you can analyze as many as you can see, view all of these modes without any problem. But the analysis is done on only 14 degenerate modes. Okay. There is a question here. I'm not sure how to access. I don't think that you have access to speak here. Okay, so another question here. Does the machine learning tool support PAM4 signal? So PAM4, as I mentioned, at this moment, the machine learning tool is released with only 2 levels. However, the multi-level signal code is available. It's just only we are in process of adding these 2 new algorithms as well as multi-level signals. What is about even modes and odd mode analysis concept? Please put some light into it. Okay, so again, it's the modes is it's produced in the multimode fiber. Is for example, the supported modes in the structure dimensions. So whatever it is possible to be supported is going to be analyzed. And they are degenerate. Like for example, if LB01 or LB11 in both ways and degenerate mode. And the spatial demultiplexer would be able to monitor both and display both in the component. Okay, so if you have any other question, don't hesitate again to send an email to myself here or to support, and we'll answer it. I thank you very much for attending the webinar, and then we will send these recordings and to all registered people, and then post them on our website and YouTube channel. Thank you very much, and have a good day.